Gotcha. All right. All right. So it is 2:30. Again, this is CSCE 310. Data Structures and Algorithms is the official title of this course. Really, it's Computer Science 3, so it's a continuation. We'll be looking more at data structures and algorithms. We'll do a quick review today, but of course, administrivia, we're just going to go through the Canvas setup, the syllabus, et cetera. We'll do a quick review, but with that review, I'm going to kind of segue on to the first topic in the course. Because we are meeting every day for an hour and a half. It's an accelerated course. It's taking 15 weeks and compressing it down into five weeks. So we're going to be going roughly 3 times as fast, 3 times maybe as difficult, versus if you were to spread that out among a regular semester. We'll get to some other differences here in a moment. But this is what we're going to do for today. So let me go ahead and switch over to, there we go. All right. Hopefully everybody has access to this. This is published. It's all in the Canvas system. You'll see that our 5-week schedule here is already determined. This is like the 6th or 7th time I've done it in the summer, so the schedule is pretty tight and pretty well regulated here. Those are the basic topics that we'll be going through day by day. You'll note that it's actually not a full 5 weeks. The last week is only 4 days. So it's only really 24 days instead. But there is a midterm schedule and a final schedule. All your homework out already. You can get started on those. At least look at them later today if you haven't done so already. So there's the schedule. The syllabus, let me go ahead and open that up. While that's loading, the venue again, we're meeting every day, Monday through Friday, 2:30 to 4:05. We might quit, at 4 or so. Right here in Architecture Hall, it goes from July 15th all the way to August 15th, which takes you up to the week. You have a week gap, and then the regular semester starts. My name is Dr. Chris Burke. You can call me Chris Burke, whatever. And I'm over in Avery 363. There's my primary contact email, but I'll talk about communication for this course in a second. My office hours are going to be every day throughout the 5-week period, from Monday through Friday, every day, 1 p.m. to 2 p.m. So before this class, I'm giving myself a half hour of slack to get over here. We do have a GTA for this course over the summer, Garrett Worka. You may be familiar with him. He administers CSCE 251. Which is the online Unix course, and so he helps me out during the summer. He's going to be holding office hours Tuesdays and Thursdays, 10 to 11, and because the SRC is closed, he's going to have to hold them in the Avery 123 Commons. You can get, if you go to Avery 123, there are several offices, satellite offices in that. The Commons means the area outside there. You shouldn't need a key or access or anything. It is locked after hours. But 11 to 10, it should be fine to get in there. Here's some resources. There's that YouTube channel. Obviously, there's nothing up there yet. But once I get home and edit this video down, it'll be made available. Unlike some of my other courses, I don't have pre-prepared lectures as well that you can watch beforehand or as supplements. But instead, I've given you several other resources down here that we'll talk about in a second. Piazza is going to be our main line of communication. I have everybody has been invited already. If you registered late, please let me know because I have enrolled everybody automatically. You should accept that invitation, and I'll be making posts to this periodically, like I've done with all my courses. If you have questions, post them to Piazza. Don't email me. You can email me, but what I'll basically do is say, that's a great question. Can you post it to Piazza? Or I'm going to take your question and put it up on Piazza, and I'm going to answer it there for the benefit of everyone. You can post anonymously. You can reply anonymously. You can post so that I know who you are, but nobody, the rest of your classmates don't know who you are. Or you can just post openly, which is what most people choose to do. So if you've got questions, please come over to Piazza. That's our main line of communication. If you email me or Garrett, we're just going to take that and move it over to Piazza and answer it there, again, so that everybody gets the benefit of the answer. There is a CSE web hand-in and web grader. If you're not familiar with those, there is programming in this course. And so, in fact, the majority of points are based on programming. You'll have to hand those in through web hand-in, and you will be grading them through web grader. They're all already set up. There are a couple of programming assignments for each. Typically what I would do is six assignments throughout a semester, but because we're compressed down, they're going to be 4, so you can think about each one of being about 150% of a regular assignment if you're familiar with the workload that I usually have. That was supposed to be the syllabus, but apparently it's not going to open up in Firefox, so let me go ahead and come over here and open it and bring it on over. Right. So we'll come back to the syllabus here in a second. Otherwise, there's department resources. If you, there's an anonymous feedback mechanism that you can contact the department chair, myself, or anybody else if you want to. There's our academic integrity policy. Everybody should have an account by CS3, hopefully. If not, like if you're a transfer student or something like that, you'll need to go to account management and get a CSE account immediately. You can also talk to me after class here today. Otherwise, there's a system FAQ if you want access to, I think, a MySQL account or you need to reset your password. There's an FAQ here. There's not a textbook, a required textbook for this course. I do have a substantial note set, and again, it's not going to download here. It's going to, but that's what I'll be working off of. It's not like a full textbook like CS1, my CS1 textbook, or my draft CS2 textbook, but it is an extensive note set, including all the pseudocode for all the algorithms and data structures that we'll go over. So you can download that and use that as you want. Again, it's completely draft, so if there's don't bother sending me typos because it's basically in note form anyway. But if you're interested in a full book or a full other course to get a different perspective, I've got several here. There are 2 courses. This course is actually split up into 2 mini courses on Coursera, and hopefully I did check on this weekend that those are still active. You don't have to sign up for them or anything. They're completely open. I think that there are videos there that you can watch as well. Like if we cover optimal binary search trees, and they cover optimal binary search trees. You can watch both. And if there's, if the recording failed, or you want a different perspective, or you think they have a better presentation of it, please go ahead and check those out. Jeff Erickson's algorithm book is a free online book, and then Open DSA, that's Open Data Structures. That's another book that has been written, and these are not my resources, these are external resources. But if you're looking for a textbook, then there's the way to go. There's where you should go. There are 2 full textbooks there, full text, not notes like my lecture notes here. If you're into reading those books, reading a full book, they're free. I think that there might be a recommended book for this course, Leviton, but I wouldn't recommend to buying it. I'm sure that there are other ways that you can get copies of the book anyway, if you want to read Leviton. LaTeX will not be required for this course, but if you want some LaTeX resources, there you go. And finally, there are assignments. We'll come. I'll go ahead and download this first one and talk about it here in a second. And again, it's not going to open up in Firefox. So I'll bring it over here. All assignments have a mixture of written portions that you have to, let's say, write some pseudocode, or you have to come up with a proof or a counterexample or something like that, as well as programming parts. So if you take a look here at the first assignment, there are the rules that you should look through. You can see here that the first 1, 2, 3, 4, 5, all the way through 8, the first 8 questions are all written questions. Develop a pseudocode, an algorithm for doing this, and analyze it. Answer this question, or provide this proof, etc. Then you've got 2 programs. One of them is a weather data analysis problem that I've used before. And then you have to compute Hamiltonian paths in undirected graphs. Those are all, those last 2 are programming assignments. So let's go ahead and let's look at an overview of the instructions. First of all, you have to show sufficient work. You have to, be clear about everything, etc. There's the academic integrity policy. You're encouraged to typeset your homework in LaTeX, but if you don't want to, that's fine. It's not required. But if you're going to, don't use Word, first of all. If you're not going to use LaTeX, then just write everything down, but make sure that it is legible. Otherwise, Garrett won't be able to read it. If you want to know how to typeset stuff for pseudocode, I use Algorithm 2E. If you want to typeset code, I use Minted. These are packages in LaTeX that you can use. TXE and PGF are great packages for drawing graphs if you want to draw a counterexample or something like that. Hand in your written answers, hard copy, with this cover page on it, okay? Because we're going to, Garrett is going to go through, give you any notes that he might have, as well as give you points based on how well you do on your on that. All right. What you do with your programs is you turn those in soft copy. All programs, all material for your programs has to be handed in electronically through web hand-in. Okay. So there are basically two. There's a hard copy written portion, and there's a soft copy stuff that you have to hand in for all of your programs. We do have a partner policy similar to 156, my 156 partner policy. If you want to, you can team up with one other person in the class. You turn in one copy, one hard copy, one soft copy. You're graded equally, right? If you get 50 or 165 out of 175, whatever it might be, you both share that exact grade, right? Don't turn in two copies. But you have to, if you're going to do it, it has to be an equitable relationship. You can't just say, you do the evens, you do the, I'll do the odds. You can't say, you do all the programming, I'll do all the written, right? Everything has to be an equal contribution. You have to work on every single part of the assignment together. You should not discuss problems with other groups or individuals, except at a high level, right? I got this exception, what does this mean? Or what IDE do you use for Python, right? And we'll talk about programming languages here in a moment. So that's the partner policy. Programming instructions are a little bit different than usual. I do not require any specific programming language for all of this stuff. The only rule that I have, and you can see it in bold there, is that you may not use Java, right? The sequence now is C, Java, and then something else. That should be something else. The reason I don't ban C is because nobody would want to do these programs in C, trust me. That you're going to be using, you want to use a lot of data structures, and C does not have a lot of built-in data structures with the standard library. You will be doing twice, 3 times as much work, or bringing in an external library and learning it with C versus, say, Python. 99% of the students that go through this use Python. That's what I would encourage you to do. If you already know it, great. Maybe you want to try something else. Maybe you want to try PHP or C# or something like that. The only condition is that it has to compile, and if it's a compilable language, and run on the CSE server. So if you've got, I don't know, I can't think of a language that we don't have. We do have Rust, JavaScript through Node.js. I don't remember, I can't think of a language that we don't have, but I'm sure that there's some esoteric language out there that's not supported on the CSE command line. That's perfectly fine. If you go to the sysadmins and say, please install this compiler for me because I want to try it in this weird language that nobody's ever heard of, great. If you can get them to do that by your first programming assignment due date on Monday, even better, but it's probably not going to happen, especially during the summer when they're really busy. 99% of the people that go through this course choose to do everything in Python, and that's what I would suggest that you do. If you want to try a different programming language, I encourage you to learn a new programming language, a third programming language that you're not entirely familiar with. JavaScript, PHP, C#, Rust is available, right? Any one of those languages that you can pick up and use for all of your assignments here. You can do a variety, right? You could say, I want to learn 5 new languages. Do one program in one, another program in another, another program in another, etc. That's completely up to you. Do realize, though, you've got a 15-week course compressed down into 5 weeks. I would learn one language and stick with it, right? So I would suggest Python. So how is this going to work? How am I going to 10 different program that you have to invoke your program. For allowing a variety of programming languages, you're required to also provide a script file named run.sh that contains the commands to compile and execute from the command line. Don't worry, because if you use any of those standard languages that we have here, we've provided examples already for you. Let's see, here we go. So if you download that zip file, there's an example for C, for C++, for C#, for Node, and Node would be JavaScript, for PHP, for Python, for Ruby, for Rust, for Swift. Swift is even supported on the CSE command line. If your language of choice that you want to use is not here, I'll work with you to develop that script. All it is a bunch of bash scripts. It's a shebang for a bash, and then you put in your compile command and then your run command. And just use the examples. In fact, we've set up a Hello World program so you can hand those in and test it out and see how it works. There are command line arguments. You just pass those through to your script. Okay? So that's how we're able to support any language that you want to use, except the only condition, again, is that you may not use Java. Right? And that's just because it used to be that CS1 and CS2 were both in Java. So you'd have Java, Java, Java all the way through all of your core classes. That's no longer the case. Now we've got C, Java. So maybe in the future I'll relax this, but it's just way too tempting to use Java here. You need a third programming language. And trust me, you need 4 or 5 programming languages before you get out into the workforce. Just not that you're going to be using 5 programming languages throughout your day-to-day stuff. You're probably only going to be using 1 programming language. It's the idea that you have a variety of skills. Yeah, I'm familiar. I can at least do a Hello World program in 7 different languages. Right? At least I can recognize one of these languages when it pops up, and I know the advantages of one and the disadvantages of the other. Where are they most appropriately used? Right? PHP is most appropriately used for back-end web development. Is mostly appropriately used for embedded systems programming, etc. Swift, where would you use Swift? Yeah, iOS programming, and that's pretty much the only way you actually use it. It might expand in the future, but who knows? Objective-C never expanded, so who knows? Maybe Swift will actually expand. Rust is a newer programming language. Last 4 or 5 years, I'm not sure how old it is, but it's an alternative. It's a system-safe alternative to C. Whether or not it gains traction, who knows? But take this as an opportunity to learn a new programming language. Keep in mind, though, that you do have to get it done. So have a plan B. All right? If you really want to learn Rust, get started right now. Some basic programs. Back to, say, Python or something like that. Okay. You also have to turn in, so you've got a bunch of points that it's worth. 10 of those points will be for 2 non-trivial test cases. For example, let's see, let's go down here. Here's a test case. Here's a Hamiltonian path test case. It's basically just the number of nodes in the graph and then an adjacency list format. You'll have to come up with, you'll have to draw your own graph. And use this formatting to encode your graph, and then that's one of your test cases, that there is a Hamiltonian path or there's not a Hamiltonian path. And we'll talk about what those are later on, but basically you'll need to hand in 2 of these input files. Why? Because our script randomly selects, I think we've got hundreds of test cases already. It randomly selects a subset of those, but also among all the test cases handed in this course among your peers, we randomly select a subset of those, and we also test on those. So if a colleague, if one of your peers hands in a bad test case, they're going to be losing points on that 10 points right there. But if it's a bad test case, sure, you can report it, this malformed input or whatever, but you won't it won't count against you if there's a bad test case in there. And if there is a bad test case in our test cases, let me know and I'll check it out. Right? But I think that they've mostly been called of bad test cases. The remainder of your points are awarded based on correctness of your program. We're not doing style. We're not doing design. We're not doing those are things that we really try to ingrain in CS1 and CS2. And if you don't have it at this point, then you're never going to get it. But no, you'll eventually get it, hopefully. All right? So the only thing that we're grading on is the number of test cases that is passed. If we've got 15 test cases and 10 of them pass, you get 2/3 of those points. Okay. All right. Otherwise, that's basically how what the homeworks look like. There is a bonus opportunity in homework 4. I think that we have like 225 points. We'll only grade it out of 175 points. So if you want to, there is some opportunity for bonus at the end here. Let's take a look at the syllabus. So I like to open up the courses with some quote that captures the theme of the course. This is an old one that's used. Can I take this problem, model it as a graph, and then I've got this entire toolbox of graph algorithms that I can apply to it to solve the original problem, right? And knowing, at least knowing what's out there, where to look next, and how to model things, that's a valuable skill that's worth, say, 8 years of experience, right? All right, so those are basically the themes to the course. Again, the textbook is only recommended. It's Leviton. Do they have it at the bookstore? Does anybody go to the bookstore anymore? Anybody? No? All right. All right, so it's Leviton. If you really want it, go ahead and find a used copy, an ancient used copy. Do not buy, I think they're on the 4th or 5th edition. Don't buy those. There's no changes. And of course, I'm sure that there are other ways of finding the book. Right, I'll leave that to you. So the course catalog description, this is as it is in the bulletin. There's my teaching style. Again, actually, I don't remember if I had updated this or not, but because we are going to be recording all of these lectures, I'm not going to be going up to the whiteboard. Instead, I'm going to be on the overhead projector here, putting as many notes as I can on here so that it can actually get captured by the lecture capture system. At the end of each major module, if you want to call it, what I'll do is I'll also scan these and then upload them as a PDF to Piazza or something so that you can have my copies as well. But you should be taking your own notes as well, all right? In case, I don't know, they get lost or something like that. And also, it's a great way to follow along. Grading. If you just put in a full faithful effort into this course, don't worry about grading. The grades will come. I always say that, but here's how it spreads out here. 1,000 points. So homework is, each one is worth 175 points. I just made them all even. So that's 70% of your grade, right? The vast majority of your points will come from homework, and homework is the most important part of this course. There will be 4 quizzes, typically on Friday. Those are all scheduled in Canvas already. Open book, open note, open computer. They're short, usually covering stuff that we've covered up till that week. There's a midterm and one final, each worth 100 points. So Exams and quizzes are roughly 30% and quizzes, midterm, and final are all written. There's no programming during the exam. They're all written. It's not multiple choice either. It's you actually write out solutions, and then you hand those in. So open book, open note, open computer on all of those. Okay. There's the scale, standard scale. Homework, quizzes, exams, etc. We've already talked about homework. Grading policy, Garrett is going to be grading everything, so if you've got a question, you go ahead and address it to Garrett first. If you can't get it resolved, then go ahead and come to me and talk about it. You can CC me on anything. You can start up a private conversation on Piazza if you want to. That includes only myself and Garrett, and I'll be able to see the conversation going back and forth. The summer session policy, again, we're taking 15 weeks and compressing it down into 5. You need to make the commitment that it's going to be going about 3 times as fast because we are lecturing every day for an hour and a half, right? And it's just as tough on me as it's going to be on you. But you have the benefit of going back and seeing the videos, assuming no technical difficulties. But there are also a couple of other major differences with a summer course. First of all, I don't know if you've been over to Avery, but you'll notice that the SRC is not open. The SRC is not open. There are no UTAs. There are no LAs, right? Learning assistants. There is no recitation. Generally, during the regular year, this course has a recitation, a 1 hour per week recitation where you go and you do your quizzes in there, or you get additional instruction, work through more examples, more exercises. That's not part of the summer course. Instead, again, we've cut it to the bone and we've compressed it down into 5 weeks. It works mostly, but if you're not able to, if you're the kind of person that needs that extra help, that needs that extra framework for getting stuff done, then you might want to take it during the regular year. Right? So make sure that you're making the commitment now that you'll get started on homework immediately, that you won't fall behind, because as another part of the summer session, there is no late homework accepted at all. If I allowed like 1 week late pass or something like that, then that would mean that you're going into that'd be equivalent to like 3 weeks of late passes in a regular semester, and you just can't fall that far behind, right? So no late work, you can no recitation, no student resource center. So a lot fewer opportunities, but you still have me, you still have Garrett, you still have each other, right? And you still have Piazza and other resources like that. Academic integrity, basics. Communication and help, again, the best way to get help is through Piazza. Where is that? There we go. Post anonymously to your peers, or post openly. Answer each other's questions, because if you're posting at 1 a.m. and I'm not there, Garrett may be there, I don't know, but one of your peers might be on and be able to answer at 1 a.m. right? And if nothing else, I'll be able to get up at 6 a.m. the next day and do it there, and answer it there while I'm getting ready. So Piazza is an excellent resource. Any questions so far? No? All right, that pretty much takes care of everything that's available on Canvas. Again, it's kind of a stripped down course because it's a summer course, and I haven't built up like the same infrastructure that I have for CS1, CS2. So if you're wanting extra help, those Coursera courses are pretty good. The Open DSA book, it's got visualizations as well. You can go ahead and check those out. Otherwise, I will be working off of my notes here. Okay. So let me go ahead, and I will come back to this, so I don't want to shut it off, but I'll go over here to the dot cam. Right, and there we go. I don't want to be bending over the entire time. So as part of this course, I generally give a review on the first day, so I'm not going to overwhelm you with a bunch of other stuff on the first day. But I do want to go through a quick review. You've gone through CS1, you've gone through CS2, so what skills have you picked up so far, right? You at least have maybe 2 or more programming languages. And at least, an academic year of experience, probably more. And if you don't have that, if you are not a competent programmer, then you're probably not going to be able to get through this course, right? And I don't think it happens that often, but some people are able to get through CS1, CS2 by relying on partners or relying on their friends or relying on somebody too much. And if that's the case, then you may not be able to complete the programming assignments. They are rather involved, right? So you at least have 2 programming languages, and now you're going to pick up a third, hopefully. So you need a good programming language background. What else would we have gone over in CS1 other than programming? Well, searching, sorting, right? So searching. There we go. Searching. What kind of search algorithms are we familiar with? Linear search and binary search. Right? Linear search just is kind of like a brute force method, which is what we're going to start with in this course. And it's linear because, well, its behavior is linear. If you have n elements and you're searching for a needle in that haystack of size n, it's going to take you up to n operations or thereabouts to find that thing. Right? Binary search exploits the fact that something is sorted. And it looks in the middle and then says, okay, well, if it exists, it's either in this half or it's in this half. So it effectively cuts it down in half each and every single time. That's a divide and conquer kind of approach. We'll talk about that as well. What about sorting algorithms? Which ones of you might be familiar with? Okay, bubble. I don't know if I cover that, but it's a terrible sorting algorithm, right? Why? It's, ooh, what's that thing? O of n squared. What is this? This is asymptotic notation. This is big O notation. That's something that you get from CS2 and from discrete math, both prerequisites for this course. What's another bad sorting algorithm? I want to go through and select the minimum and then put it at the front. Selection sort. Right? And that's also order n squared. Right? What is a bad sorting algorithm that's kind of in between, or not as bad as these, a little bit better? Insertion sort. It's going to be order n squared, but if you actually analyze it, there's going to be a factor out front here of about 1/4, right? About. And which is much better than selection sort, where its factor out here is 1/2, and bubble sort, there is no factor out there, it's 1, right? So in practice, insertion sort works on small arrays. Those are all sorting algorithms. What are good sorting algorithms? Give me one. We have fast sorting algorithm. One that is quick sort, or merge sort. Both of these are, again, kind of like binary search. They're divide and conquer. You divide it up into 2 arrays, and then you you recursively sort each one in some ways. Right? You've also got, say, Tim sort, which is basically kind of a merge sort. All of these are going to be order n log n. Right? How much better is that than n squared? Right? Well, you're changing one of those linear terms into a logarithmic term. So if you go from, say, linear down to logarithm, how much of a speed up is that? How would you characterize that? Is it twice as big? Or twice as fast? 3 times as fast? Linearly fast. I divided by n or something. That's too much. This is exponential. This is an exponential speed up, right? Why? How could I go from log n back to n? What would I have to do? I would have to raise it to an exponential, right? So this is an exponential speed up here. So you can look at it from that perspective. This is still polynomial. This is still polynomial. But if you look at this one term here, that's an exponential speed up in that one term. Right? So searching and sorting algorithms, and also a little bit of algorithm analysis. Right? Bled through, dang it. Right? Oh well. What else? So you've also seen algorithms and algorithm analysis. You've seen how do we express algorithms in general, independent of any particular programming language? pseudocode, fake code, right? And there's no rules for writing fake code because if there were rules, then it would be code, right? Pseudocode, analysis. There's usually a 5-step process. Remind me, what is it? You identify the input, and that's usually done by good pseudocode already. 2, you identify the input size. 3, you analyze the algorithm with respect to, WRT, with respect to the input size. And you come up with a function, right? I'll call it F here, that maps an input size to some, say, T sub n, right? So, well, I shouldn't express it like this, but it's a mapping, right? This is the input size. And this is some resource. And implicitly here, what resource am I talking about if I call it T? Time, right? There are lots of computational resources. It could be time, it could be memory, it could be power, right? All of those things are interrelated to each other. So what we look at with respect to, you know, an abstract notion of what algorithms are, as we looked at time and sometimes memory, right? So how many steps does it take to execute your algorithm? In fact, darn it, this should be 4. Darn it. What is 3? What do I mean by steps? You have to identify. No, this would be the number of operations, but if you're going to count operations, what do you have to decide first? An algorithm could do a lot of things. It could do an addition, it could do a multiplication, it could do a comparison, right? It could do all of these things. You need to decide on one. You identify the elementary operation because you want to simplify that. You don't want to add up, I mean, if you're an engineer, sure, go ahead and add up the number of clock cycles that it has to go through. Add up the number of assembly code instructions that gets executed, something like that. If that's an engineering problem. But we don't want to have to look at any particular platform, at any particular computer, at any particular time in our history. Because algorithms existed way before modern computers, right? Euclid's algorithm is thousands of years old. It takes exactly the same number of steps 2,000 years ago as it does today. Even though it's on a computer, computers can do those steps a lot quicker. We still need, it still takes the same number of steps. So we need to define what is that step, what do we mean by step? Well, we need to define, I'm going to analyze it with respect to this elementary operation. Right? And then 5, we provide a big O, or since everybody's taken CSE 235, discrete mathematics, what's another way of expressing it? Big theta characterization. All right? Like we did with selection sort. We said that it was order n, it's actually theta n, if you want to be more accurate. And these are, well, these two are going to be theta n log n. Quicksort can devolve, and so we'd only say that it's order n log n in the best case. Right? There are lots of caveats there. So that's algorithms and algorithm analysis, but you've also seen basic data structures. What data structures have you seen already? From CS1, CS2. Stacks, queues, and variations. For example, a deck can be either. A deck is more general. You can work from both ends. What's another special kind of queue? A priority queue, so PQ, right? Priority. And what's a nice way of implementing a priority queue? A heap, right? You've also got trees of which a heap you can represent a heap as a tree. You've got graphs from 235. Trees are graphs. They're a very special kind of graph. They're acyclic graphs. But you can also have general graphs. Directed graphs, undirected graphs, weighted graphs, named graphs, et cetera, et cetera, et cetera. Right? Multigraphs, pseudographs, et cetera. Right? You should. That's all on my list here. You should have some basic, discrete math. Right? For example, proofs and logic, as well as graphs. What else did you cover in 235? Well, algorithms and algorithm analysis as well. You get another treatment of that from there. What else? What's the coolest thing that you remember from 235? Nothing cool at all. Most interesting, if I phrase it like that? Okay, asymptotic notations. Like the little asymptotics as well, right? The small omega, small o, theta, big O, omicron, big omega. Right? What else? Oh, okay, master theorem. Where does master theorem come in? Algorithm analysis, what kind of algorithms would come into master theorem? Recursive algorithms, right? So you can use the master theorem to set up a recurrence, and then not having to solve that recurrence, you can use the master theorem to come up with a big theta or big O characterization of that thing, right? Okay. Well then, let's take what we've learned so far, and let's go ahead and solve a problem. So here's a more formal way of presenting a problem. Probably seen this problem before. In any case, it's going to be such a simple statement that you'd be able to solve it really quick, right? It's called the closest pair problem. Right? So given, we always identify the input when we have a problem statement here. Given a collection of points in R2. Right, what do I mean? What is R? That's all the real numbers. So what is R2? It's the Cartesian product. Right? You remember Cartesian products of sets? That's another thing that you get in 235. If I've got a set A and I do Cartesian product with B, right, I get pairs A and B. Well, if A and B are both the reals, and I Cartesian the product of the reals with the reals, I don't call them A and B, I call them X and Y. Right? What am I talking about here? What is this thing? What do I get when I take the Cartesian product of the reals? The Cartesian product of the reals. I get the Cartesian plane, right? In other words, this thing right here, X and Y. Right? That's how we define the plane, the Cartesian plane. So given points in the Cartesian plane, we'll even give it a name. A is equal to x1, y1, comma, x2, y2, comma, dot, dot, dot. And then say that we're given n points. There we go. And we can even call them P1, P2, P3, et cetera, if you want to. Then determine or output the two closest points. Do we give them names? Piece of A and piece of B in A. Right? So that formal statement there is, given these dots, right, all you have to do is determine which two dots are the closest together. Right? Here's my Cartesian plane again. If I just draw a bunch of dots all over the place, then what should I be able to do? I should be able to find these two that are, I intentionally drew them the closest together and then drew everything else all over the place. Right? Very, very simple statement. Now let's go ahead and come up with a solution. So help me out. help me to write what? Pseudocode, an algorithm. Right? So here is my algorithm. I identify the input, a collection of points, A equals, and here I'll call them P1, P2, dot, 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 P sub n. There we go. Yell at me if it ever goes off screen here. Right? And I'll output the two closest points in A. And I like to do this because it already takes care of the first couple of steps when I do go ahead and do algorithm analysis. Step one, I need to identify the input. Hey, already done. Right? It's a collection of points. It's a set of points. Step two, identify the input size. How big is this? There are n of them, right? So you'd say, well, it's n. Right? Now, granted, a point is two numbers, right? So you could say that, well, it's 2n. We kind of tend to not consider that because 2n, when you get down to step 5 where you provide an asymptotic characterization, that 2 is going to disappear anyway, so who cares? Right? It's the size or the cardinality of this set. Right? All right, so help me out. If I've got a bunch of points, what do I need to do? Here's my points again. I'll say start with this point and then compute the distance here. Okay, there's one distance. Compute the distance there. There's another distance. And it looks shorter to me, so maybe we'll update the minimum distance that we found so far, and there it is. Right? Okay, well, that one's even closer, so I'll update there. Right? That one's further away. Okay, so I won't do that. And I'll go ahead and take this point and compare it to all the other points. Then I'll move on to another point. And I'll compare it. Right? So, how do I codify that here? Remember, it's pseudocode. You can cheat, right? So, for each pair of points, P sub A, P sub B, in, I'll use mathematical notation, A, I will compute the distance between them, right? Now for that one, I don't want to just say, well, compute the distance between them, right? That's too much plain English. How do I compute the distance between 2 points in a Euclidean plane? Is there a name for it? The distance function, right? Square root, I don't know if there's a name for this or not. Euclidean distance function, I guess. All right, x sub A minus x of b. It's the difference of your x coordinates squared plus the difference of your y coordinates squared. The whole thing taken to be square root. There's your distance. Right? I left myself some room up here. Why? I need to compare this distance. If this distance is less than the minimum distance that I've found so far, I'll give that a name, d sub min. Right? Then I need to update 2 points. Right? I need to say d sub min is going to take on this new distance. And also, I need 2 points now, p and q. P will be updated to p sub a, and q will be updated to p sub b. Right? And then at the end of this for loop here, I will output the 2 closest that I've found so far. Output P and Q. Maybe I should have given them better names or something. Right? But why did I leave myself some room up here? Yeah, what is the initial minimum? Well, I could just go ahead and jump to 2 random points and say, okay, well, that's good enough. Right? Or, again, it's using pseudocode here. I could set it to something so large that any actual 2 points will be less than that. What should I set d min to? Infinity. Positive infinity. Right? Don't want a negative infinity because then everything will be less than that. Right? All of our distances will be non-negative. You could have multiplicity here, that you could have 2 points that are the same, and then the distance between them is 0. And that's those two coincident points are the closest 2 points. Excellent. This is excellent pseudocode here. But it's also cheating pseudocode. Right? How could I translate this in practice? So let me go ahead and bring this over here. Right? How do I translate that loop for each pair of points? Well, first of all, let me go ahead and set up some points here. 1, 2, 3, 4, 5 points. Right? 1, 2, 3, 4, 5. Now, how many iterations of that loop am I going to go through for this particular example? Right? When I compare 1, I need to compare it to, I'll look at this distance, I'll look at this distance, and this distance. Okay? How many distances was that? 4. Right? 1, 2, 3, 4. All right, well, now when I move on to this, so I've compared everything here. I'm done with 1. When I move over here to 2, do I need to compare it again to 1? No. I just need to go 3, 4, and 5. So there are only 3. When I move on to 3, I've already compared it to 1 and 2, so I only need to do 2 more. Right? When I move on to 4, I just need to compare it to 5, so there's 1 more. And when I move on to the last one, the last point here, I've already compared it to all the other points, so I don't do anything there at all. Right? So how many distance computations am I going to do total here? Oh, how many? 4 plus 3 plus 2 plus 1? 10. Right? What does that correspond to? Again, this is a review, 235. What would you be looking at here? All pairs of points. What kind of a combinatorial concept is that? If I've got n points, p1, p2, p5, and I'm going to be comparing them pairwise, what do I need to be looking at? Say what? All pairs, right? That's what my pseudocode says, for all pairs of points. How many are there? In general, if I had P1, P2, all the way up to Pn, how many would I be looking at? If I have n points, how many of them do you need to choose to get pairs? To get a pair, how many do I need? 2, right? It's the exact same thing, but that's only because it's symmetric. Right, so that's cheating. That's a different perspective. That's like, all right, here's 1 point. Now I need to exclude the rest, or here's 2 points. Now I need to exclude all the others because I'm only focused on that. And that's the other way of looking at it. But n choose 2, right? This is going to be equal to the number of pairs, right? Without order. In other words, if I look at P1 and P2, I don't need to also look at P2 and P1. If order did matter, what would I be looking at instead? I wouldn't be looking at n choose 2. I'd be looking at n. All right, now I need to compare it to all of the others, and I do need to compare 5 to this. So this would be 4. And then this one, I do need to compare it to 1 still, so it'd be 4, 4, 4. Right? And by the time I get to this one, I would have compared it to everything else. So this is like 16 instead. This is like n squared minus n in general. Right? That's not what this is. What is this? N choose 2. Do you remember, in general, what is n choose k? You've got n distinct elements, and you need to choose k of them. How many ways are there of doing that? N factorial, all over, n minus k factorial, k factorial. And I won't derive this, that's 235. But if k is 2, what happens here? N minus 2 factorial, all those factorials cancel out, and you get n times n minus 1. K is 2, so you have 2 factorial. What's 2 factorial? It's just 2. Right? So this is n times n minus 1 all over 2. Right? That's the number of distinct pairs. Okay? So it's not exactly n squared. If n squared would also be, well, I need to compare P1 to itself. Obviously, you don't want to do that because any point, the distance to any point to itself is 0, and that's not part of the problem you want to solve. Right? So there is a nice little reminder of, oh, well, if I need to generate all pairs, here's my pseudocode for doing it. Here's the number of ways that you do it. Now, if you were to actually program this in, say, C or Java, how would you go about doing it? All pairs. Does C or have a for each loop? For each, can you write in C or Java for each pair of points PA, PB? No. You can't even do that in Python, and Python is supposed to be the pseudocode, right? It's not exactly pseudocode. Right. So, nested for loops, right? For I, all right, let's do this proper. For int I equals 0, I is less than something, I plus plus, right? And open that up. I is going to be my first variable. In other words, I'm going to go a piece of I, right? And it's 0 index now because we're in a real programming language, right? And then you have a nested for loop inside that. Int j equals, where do I start that? If I've got, again, if I've got 1 and 5, do I also need to do 5 and 1? Nope. So I will start it at I plus 1. Right? Because if I compare, here's j, if I compare it to everything after, here's I, and I'll start j over here because I don't need to start j and compare it to everything that came before it, because that happened in a previous loop. So I'll start j plus 1. I, or j, is less than something, j plus plus. And then I won't bother with the rest of it. I'm a real coder here. I'll put in a to-do. Right? This is what I want to focus on, though. What do I go up to on each one of these? Well, yeah, n minus 1 on the first one, y. And then n up here, noting that these are both strictly less than. So this will go all the way up to and including the last one. This one will stop short. Right? Why? If I've got 5 of them, I need to compare P4 and P5, but I don't need to compare, I don't need to go all the way over here, because if I go I all the way over here, what is j? Well, it's fallen off the end already. Right? So I'm stopping short here. In other words, if I've got n is 5, this is going to be 0, 1, 0, 2, 0, 3, 0, 4. Right? There's the first 4 that we compared. Then it will be 1, 2, 1, 3, 1, 4. There's the next 3. Remember, we already determined this, right? Graphically, there's 4 of them, 3 of them, 2 of them, 1 of them. It's going to end up being 2 and 3, and 2 and 4. Right? And then finally 3 and 4. Again, there's 0 index, and so I will be doing 4 of them, 3, 2, and 1. And so that's how I can translate this loop over here. Right? Remember this, because I'm going to ask you at the end, what if I wanted to look at all triangles? Right? So 2 points makes a line. 3 points would make a triangle in the Euclidean plane. And I want to know, I can compute the area of that triangle, and I want to find the smallest triangle. How would I end up doing that? Okay? And we'll come back to that here in a second. As part of the review, though, I want to go back to my pseudocode, and I want to analyze it. Right? We already did the first 2 steps. Step 1, what's the input? It's the collection A. Right? 2, what's the size of the input? Well, I conveniently gave it a name already. It was n. Step 3, what's my elementary operation? So I can go ahead and number these lines for you. 1, 2, 3, 4, 5, 6, 7, 8. Doing a lot of stuff here. For example, we're doing assignment operations. Right? We're doing something that's necessary to the control structure of the algorithm. When we actually write this in code, obviously we're doing an assignment, we're doing a comparison, we're doing an increment, an addition, right? Don't worry about that stuff. That's necessary for the control structure of the algorithm. Look at what the work you're actually doing in the algorithm is. Well, again, it's an assignment, who cares? Doing a lot of math here. Subtraction, addition, subtraction, multiplication, multiplication, square root. We're doing a comparison. And based on that comparison, we may be doing 3 assignments. Which one of these is best? Which one should we focus on? I don't want to add up, well, this is how many of this thing we do, and this is how many of this thing we do, and this is how many of this thing we do, and I can come up with this nice weighted linear function, and then I can plug in the number of CPU cycles for each one of those particular operations, and then I'll get an answer out, and it give me an actual, it'll take you 45 milliseconds on this. That's not what I care about. What I care about is the growth rate of this. If I put 1,000 points into this algorithm, how well is it going to perform? Then if I put 10,000 points into this algorithm, how well is it going to perform? On up to, well, if I put 1,000,000 points into this, how well is this going to perform? Okay? So which one of these things should I focus on? Votes. Nobody has votes? What's your favorite mathematical operation of this thing right here? Any? Okay, comparison, right? You could go with comparison. If you were an engineer, which one of these would be most expensive on your CPU or on your GPU or something like that? Would a comparison be more costly? A comparison in a jump, right? Would that be more or less costly than multiplication? Less, all right? So this would be, if you were an engineer, right, and you had an engineering question, right? I want to focus on this. I want a GPU that will be optimized for multiplications because that's more important, right? And certainly multiplications are going to be way more important than additions and subtractions. What's going to be even more important? What's going to be if you were to run this on an actual GPU on your NVIDIA or something like that, which one of these is going to take the most time? What do we call that? The radical, is it? Right, the square root operation, right? So you could say, oh, the square root operation on line 3. When you said the comparison operation, that's not a wrong answer, right? There are some less favorable answers, like I just want to count that one, that initial assignment operation up there. Oh, it only cost me 1 unit, right? No, that's not how it works, right? You're doing you're doing a loop and you're doing stuff inside that loop. But between a square root operation or a comparison, they're going to be the same because you execute it once with respect to each iteration of this loop and once with respect to each iteration of this loop. And so, you know, it's a wash. You're doing it once here, so it's going to be equal at the end of the day. When you start thinking about engineering problems and actually running this on actual hardware, then you start to say, okay, well, yeah, there is a big difference there, and I need to make sure that it'll run well over here. Right? But let's go ahead and just say the comparison on line, what was it, 4. Okay, that's good enough for me. Now 4, how many times is line 4 executed with respect to the input size n? Well, that's why I went through this already. Our pseudocode says do it for as many pairs as there are. Well, how many pairs are there? N times n minus 1 over 2, n choose 2. In fact, I'm just going to leave it like that. N choose 2. You can derive that and get an actual answer out of that if you really want to, but I like to leave it in that general form. Right? Anybody who knows, has taken 235 would be able to, you might not remember it off the top of your head, and that's completely fine, but you just need to go back and, okay, what was it again? N squared over whatever, okay, and simplified, okay, it's n times n minus 1 over 2. Right? N times n minus 1 all over 2. Right? So, last step, this is clearly theta of what? What's the most important term here? 1/2 n squared minus n over 2, right? So constants don't matter. Lower order terms don't matter. What's left? N squared. Kind of like those terrible sorting algorithms, selection sort and what else? Bubble sort, right? So sometimes you have to provide a full analysis of this, like a limit method. In fact, since it's a review and since we've got time, I think I have to wake up my computer here to see the time. Yep, Good enough on time? Remind me, how do I prove big O or big theta? I set up a limit. So what my claim is that n times n over minus 1 all over 2 is big theta of n squared. How do I prove that? I set up a limit. As n tends towards infinity, you all did this in 235, right? Yes? Okay. So we don't do this in 156 because it requires limits, but n times n minus 1 all over 2 all over n squared. Well, if I expand this out, what do I get? I get 1/2 n squared over n squared. And I don't lose your limit. And tends towards infinity, blah, blah. And then I can split, the sum of limits is equal to the limit of sums as long as they converge. They will converge here, so I'll split it up here. Limit as n tends towards infinity. The other lower order term is going to be n over n squared. And then there's 1/2 out front here. I'll just put it down there. Okay? That's just algebra right there. And the fact that you can split up limits. So what's this first limit? What's going to happen to n squared over n squared? Cancel each other out. And all you're left with is 1/2. What's going to happen here? Forget about that 2 for a second. This cancels with this. And so you're left with the limit of 1 over n. Right? So as n tends towards infinity here, what's going to happen to this ratio? It's going to go to 0. Right? It's going to converge down to 0. Right? Now, if you were in an analysis course or if you were in calculus land, then you might have to prove that using a delta epsilon proof. Here, this is obvious, right? You don't have to prove that, right? It's just 0. And since it converges to a constant, we know that this implies that it's going to be big theta. What are the other options? What if it converged to 0? What would that imply? It means that the denominator is growing faster than the numerator, so what happens? This is much bigger. This is going to be big O of that, right? That would imply big O. What if it diverges? If it diverges, then the numerator is growing faster than the denominator, and so if it diverges, goes off to infinity, what does that say about this versus this? Big omega, right? So if you're hankering for a review, check out the CS2 book that I use in 156. It does go into the limit method and all that stuff. But go back here. It's clearly theta of n squared, right? You could say big O of n squared too. That's not wrong, but this is a stronger statement because big theta implies big omega and big O. O is omicron, right? What if you had done it with respect to the actual code here? How would you have had to do step 4? How you would have had to do what? You would have had to set up a sum, right? So we're doing one operation here. Here's the operation in here. We're doing it once for every time we run through this for loop. So you'd have to set up a summation of j running from I plus 1 all the way up to n minus 1. Right? Then you'd have to set up a summation for this, I equals 0 up to n minus 2, because we're stopping short, remember? Right? And then you'd have to solve this summation. As a really quick review, do you want to do that? Do you want to solve that? Okay. Let me rewrite it over here. The summation of I equals 0 up to n minus 2. Summation of j equals I plus 1 up to n minus 1 of 1 is equal to, let's take care of that inner summation first. 1 plus 1 plus 1 plus 1, how many times is it? We start at I plus 1 and go up to n minus 1. So we skipped the first I of them, basically, and we went up to n minus 1. So how many is that? If we went up to 50, right, and we skipped the first I of them, then it would be 50 minus the first I of them, so 50 minus I. Well, this is just n minus 1, so minus I. And don't lose your outer summation. I equals 0 up n minus 2. So just like the limit of sum, or the limit of sums is equal to the sum of limits, the sum of sums is equal to the sum of sums. In other words, I'm going to break this up. Right? I equals 0 up to n minus 2 of n minus summation of I equals 0 up to n minus 2 of 1. And I'm taking these minuses out here. I equals 0 up to n minus 2. I said minus 1, but it was minus 2, and I wrote it correctly. Right? So this first one is n plus n plus n plus n. How many times? Be careful, because it starts at 0. N plus n plus n, how many times? N minus 2, but we started at 0, so there's an extra one. So n minus 1. 1 plus 1 plus 1, how many times? N minus 2, but we started at 0, so an extra. N minus 1, and ones, basically. Right? What about this last one? Well, if we start at 0, it's not going to matter. So let me go ahead and start it at 1. 1 plus 2 plus 3 plus 4 plus 5, all the way up to n minus 2. Does that look familiar? That's Gauss's formula, right? And Gauss's formula is what? N times n plus 1 all over 2. But we've got n minus 2 up here, so it's going to be n minus 2 times n minus 2 plus 1, n minus 1, all over 2. Right? So you can simplify this, okay, let's simplify it. So what will this be? N minus 1 factored out of an n minus 1, n minus 1 squared, right? Minus n minus 2 over n minus 1 all over 2. I can factor out another n minus 1, and I get, and then I want to multiply that by 2 to get it over here, so minus 2 n minus 1 minus n minus 2 all over 2. Am I right so far? Yep, I think so. Darn it. Shouldn't have, either I made a mistake or I'm just not seeing how to simplify it, but what should I end up with? Dot, dot, dot. Or another way of saying that is? Right? There you go. Why, did you already simplify it? And get this? Okay. I might have screwed up here too, right? And it's on the video. I can go back and check and see where I screwed up if I did. Otherwise, I'm just not seeing. I probably don't want this as a separate term. So if I just put 2 and 2 here and then factored it out, it would probably look a lot better. I'd probably end up with like n minus 3, and then I can simplify it or something. But you'll end up with something like this, right? Or you can put it into Wolfram Alpha and say simplify, right? And that's what I would do. All right, so that was step 1, 2, 3, 4. Okay, so how bad is this, right? This is an order n squared algorithm, right? So what's another way of perspective of looking at that? I want to make sure I've got time, good. Right. So how bad are n squared algorithms? Here's one way of looking at it. If I go with an input size of n, well, it's going to, I'll ignore lower order terms, I'll ignore the constants out front. This is the number of operations, okay, n squared. I'm interested in the limit, right? This is why we use the limit method on these things, because what happens when your input size grows? What happens when, say, it doubles? Then what kind of work are you doing now? 2n squared, which is going to be equal to, what happens to that 2? 4n squared. In other words, it goes from this to this. 4 times as slow, right? Another perspective, What if I go up an order of magnitude? What if I go up to 10n? Right? I go from 1,000, like I said before, up to 10,000. How much of a slowdown, or how many more operations can I expect out of this? It's going to be 100 times slower. Right? Now, okay, well, yeah, it's going to be slower because it's a bigger input. Right? How bad is it in practice, though? So you might be able to wave it off. Well, that's just theoretical. You know, it's not that bad. Here we go. I'll go ahead and get rid of all this stuff and focus only on this nice little C program here called closest pair. Right? I've done demonstrations like this before. What it does is I've got a main here that has it's a clock ticker. It calls this function called closest pair, and it returns the minimum distance between them, between that array right there. You can see it up here. At least it's where is it? Closest pair. It takes an array of points, right? And a point is an XY structure, and then I generate a bunch of random points. That'll be part of the input. I'll generate 100 points and 1,000 points and see what this looks like, right? And then it reports at the end how long it took, right? So it randomly generates a bunch of points within a range, and then it does this brute force algorithm that we just developed. You can see that right here. Where is it? Let's go down here. What is it doing? It's doing 2 for loops, right? And then it does a comparison. It calls this distance function. This distance function is the square root of the differences multiplied together, differences of multiplied together, right? So let me go ahead and compile this. Oh, is it closest pair? There we go. Right. All right, I'll run it, and by default, I think it does it for 100 random points. That's measurable, right? It's 0.000055 seconds. So let's get this up here. Let's at least do 1,000 points, right? That took less than a second still, right? 0.005 seconds. Let's get this up to something where it's actually measurable by human perception, right? Because that's immediate, basically. 10,000 points, right? There was a little bit of a delay there, right? By the way, the timer is not timing the generation of the random numbers. That's also taking some time. I only start the clock after that's done, and then I stop the clock after I find the closest pair. That took 0.42 seconds, so a little less than half a second. For, what was it, 10,000? If I double that, what should it be? Remember, it was, if I doubled the input size, it went up to 4 times as slow, right? 4 times as long. So 4 times as long here would be what? 1.6 some seconds, right? Because that change. Oh, wow. Execution time 1.6. Good prediction, right? What if I up it again? What if I go up to 40,000? Again, 4 times as big, so it's going to be something like a little less than 8 seconds. There you go, it was 6, right? 6.33, okay. What if I went up to 80,000? Even longer, how much longer? 4 times as long. All right, well, let's go back to the beginning here after this is done executing. It was a half a second for 20,000. All right, I don't care anymore. For 20,000, so let's go ahead and go with 200,000. All right, there we go. How big is that going to be? Or how long is that going to take? 100 times a half a second is going to be about a minute, right? But 200,000 points, is that big data? Not at all, right? I'll let that go. And I've got, in the background here, I'll bring it over, I've got Wolfram Alpha. Right? All right, so we'll get a nice little answer out of this. What if I went to, I don't know, real big, tell me, what is big data? How many points would be big data? 1,000 obviously is not big data, right? 200,000 is not big data. Maybe 1 million is big data? That's too many. 1, 2, 3, 1, 2, 3. It's 1 million points. big data. Put that into perspective, right? Everybody thinks in terms of, say, hard drive size. 1 million points. How many megs of data is that? Well, there's 8 bytes for each double, 2 doubles for each point, so 16 bytes per point, and there are 1 million points, 16 million bytes. How big is that? We don't know sizes? That's less than 16 megs, right? Is 16 megs big data? No. Is 16 gigs big data? It's what? Yeah, what's the minimum threshold, right? I've spoken to people that done like data crunching on just data in universities in the 50 states. And they thought that was big data. They had like 10,000 pieces of data. It was big data to them because if you have 100,000 points in Excel, it grinds to a halt, right? And so, yeah, oh, this is terrible. If you have a real programming language on a real hardware, right, then that's not big data. So 1 million's not big data. By the way, that's a better way of writing it. Here we go. There we go. That's not big data. 1 meg, 1 gig, we said that wasn't really big data. My hard drive here is like 4 years old, and it's got 500 gigs on it. Come on, right? I just bought well, I guess my SSD. I bought, so I have a bunch of hard drives sitting on my desk, and there was one from like 10 years ago, and it was like, I think it's 500 gigabytes, and it was huge. Right? And then I've got another one that was 4 terabytes, and it's getting smaller. And I've got one that's 4 terabytes, and it's even smaller. They're all Western digitals. And then I've got an SSD that's it's only half a terabyte because their SSDs are expensive. But it's no bigger than this. Right? So, big data, not big data. What's next? That's 1 gig. What's next? All right, terabytes. That's getting, for commercial, stuff that you buy at Best Buy, that's getting up there. That's still only 1 terabyte. You can, again, I have 1 hard drive on there that was 4 terabytes, right? And it's only this small. Right? What's next? Petabytes, right? All right, I'll start to agree that that's kind of big data. Let's assume that we have that many points, okay? Now, I was able to do, how many was this? I forget now. 200,000. I was able to do 200,000 in about 3 minutes, right? So how long would it take me to do big data with this algorithm? I was able to do 200,000 in 3 minutes. So that's going to be, and then times 3, that's going to be the number of minutes. Oh, sorry, should be times 3. There we go. That'll give me the number of minutes, right? Okay. How many minutes in an hour? 60 minutes in an hour. How many hours in a day? 24 hours in a day. 365.25 days in a year. So how many years would it take me to do this if it were, if I went ahead and did it like this? I think I have this as a long, but I'm not sure. One, or a floating point number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Assuming that it would actually run. Okay, segmentation fault. It can't create that many random points and store them in memory. But assuming that it could do that, how long would it take? In case that's too small for you. There we go. So, 3,000 what? Years. All right? I can almost guarantee you that I could get this done in at most a week with a better algorithm. Right? An algorithm that was not n squared, an algorithm that would be, say, n log n. Right? Okay? So, the takeaway on this is, again, you can program every day of your life for the next 10 years, or not every day of your life for the next 10 years. Not saying you're going to only last another 10 years. But you can program every day for 10 years, or you can program every day for 2 years and take a data structures and algorithms course, because it's this kind of stuff that puts that kind of stuff into perspective. Right? One last thing that I want to do today is ask you another question that will put this stuff into perspective. This was for pairs. Okay? What if I wanted to do triples? I wanted to do, here's 1, 2, 3, 4, 5 points. How many triangles can you draw here? There's one. There's another. There's another. But there's also another, right? So how many different triangles can you, this triangle right here, this triangle, each one of those triangles. How many triangles can you draw with just 5 points? How would you end up doing that? 5 points, how many do you need to choose to form a triangle? Choose 3. So this is going to be what? 5 times, or 5 factorial. Well, here, let's just do it this way. This is going to be n times n minus 1 all over 2. No, it's not. Sorry. It is. We do have to expand this. N factorial over n minus k factorial. K factorial. Well, n is 5, so 5 factorial all over 5 minus 3 factorial is 2 factorial, then 3 factorial. The 3 factorial cancels out with all this, so this is going to be 5 times 4 all over 2 factorial is 2. So this is going to be equal to 10. There would be 10 triangles that you could potentially draw here. Right? That's just the math. How would you end up doing it as pseudocode? Well, again, pseudocode you can cheat. For each triple, PA, PB, and PC, right? Then you can compute whatever. But if you were to do this in a real programming language, how would you end up having to do it? With 2 of them, we said 2 nested for loops. With 3 of them, how are you going to do it? 4, 4, and 4, right? For I, running from something j and k, ... Right? Do it for 4 now. Piece of D. What are you going to have to do if you take this kind of approach? Another for loop. For I, j, k, l, ... What if I said do it for any and all k? In other words, I want you to take n and k at both as inputs. And you have to generate all subsets of size k. Are you going to be able to do it like this? That's actually a good question. That would be get you into metaprogramming, where you would have to program something to write another program. And you could do that. You could write a program to output a bunch of C code. And if I gave you k, then you could increment your characters in the ASCII text character set. And so you could write a program to generate another program to do this, right? But that's the cheater's way out of this, right? What I want to do is, given n and k, how could you do this without having to hard code a bunch of for loops, right? And maybe you've seen it before. If I've got n choose k, this means that all subsets of size k. Well, how could you do it? If you wanted to do it for all k, if you wanted to do it for k equals 0, 1, 2, ... all the way up to n, you can generate all subsets of size n. What is it going to be? How many of them are there? N choose n? There's only one of them. It's the entire set. Right? So hopefully you've seen this before, but did you have to do this in 235? Did you have to write a program to generate all subsets? No? Okay. Then I'll show you how to do it. In fact, I'll show you 2 ways how to do it then instead. Even if you've seen it before, I'll show it to you again with a different way of doing it. But this gets into brute forcing, right? If I've got a problem where I need to generate all subsets, or I need to generate all combinations of a certain size, all subsets of size k, right? How do I do that in general so that I can then apply that solution, that general solution, to a specific problem, like all closest pairs or all triangles, right? What other kind of combinatorial objects do you remember from 235? These are unordered. What are the ordered versions of these things? Like 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1. What else is there? 3, 2, 1. All right, and 3, 1, 2. What are these called? These are permutations. That's what we're going to be focusing on this first week. How to generate combinatorial objects algorithmically. Why you would not want to do that. How many of them are here? How many permutations are there of n objects in general? N. So n here is 3, and I generated 6 of them. So n. That'll be combination subsets. N factorial, which is even worse, right? 2n. This is much greater, right? So generating permutations, generating combinations, generating other things. Why you would not want to do it, of course. I have a 52 card deck. How many permutations are there? 52 factorial. Would you generate those to analyze them? We'll talk about that tomorrow. Right? All right, and so brute force algorithms for the first week. I would encourage you to go home and check out